Good evening, friends. Welcome to 360DigiTMG. So, in the previous lecture, we have understood about what is model compression. We have gone through various techniques of model compression as quantizations. So, after that, we have understood about how quantization works, the types of quantizations like post-training quantizations, quantization-aware trainings, dynamic quantizations, and we have understood about the differences like what quantization aware technique do and what post-training quantizations do. Then we have understood about GPTQ, that is global post-training quantizations. Then we have gone through the process of GPTQ algorithm where it uses the lazy batch updates, and we have gone through the summary of the full algorithm. And we have understood about the benefits of GPTQ. Okay. So, and then we have understood about GGUF, that is Global Gradient Uniformity Framework. And we have understood about how GGUF works and the key benefits of GGUF. So today is our topic, which is Activation Aware Weight Quantizations, that is AWQ. So our Activation Aware Weight Quantization is a recent technique which is gaining tractions in the field of model compressions. It tackles the challenges of reducing model size and memory footprints while preserving accuracy, primarily focusing on large language models like Lambda and Jurassic 1 Jumbo. The basics of weight quantizations are, so weight quantization is the process of reducing the precision of parameters. Okay. And like parameter in the sense weights in the neural networks. Okay. And it typically have a weights which is represented as a floating point numbers. Okay. With relatively high precision, often 16 bits, or we can say 16 FP16s. However, this level of precisions will require significant GPU memory resources. Okay, so if you have a significant GPU resource, you can use this. Okay, then weight quantization aims to represent these weights with a smaller numbers of bytes, such as 8-byte or even 4-byte integers. This reduction in precisions can significantly reduces the memory requirement, making it feasible to deploy the LLMs on smaller numbers of GPU also. Then the role of activations in weight quantization. So, AWQ takes the concepts of weight quantizations to the next level by considering the activations of the model during the quantization process. In traditional weight quantization, the weights are quantized independently of the data they process. In AWQ, this process takes into account the actual data distribution in the activations, which is produced by the model during interference. Okay. Then how this AWQ is work? Or what we can say first, why this AWQ is important firstly. So this is a model compression technique as we know. So as AI models, especially like LLMs, are Lambda and Jurassic 1 Jumbo we are using, right? So becoming larger and more complex, it becomes larger and complex. They require significant memory and computational resources. And for that, what we are using, we are preserving our accuracy by using the key benefits of AWQ. Okay. Then how this AWQ works? So AWQ works by taking into account the activation values, the outputs of the neurons in the models during the activation process. By being aware of these activations, AWQ can make more informed decisions about how how to compress the weights of the model, like how we can reduce the weights, or how we can compress the weights. So this means it can prioritize keeping the most important information while discarding the less critical details. Okay. So this is our, so what we are doing here, we are collecting our activation strategy and we are searching for the weight quantization parameters. Then we are quantizing. With the quantization parameters in place, the model weights are quantized using a reduced numbers of bits, as we can see here. Okay. Then there are certain benefits of AWQ, like it has high accuracy, maintains comparable accuracy to full precision models, even with aggressive quantizations, that is 4-bit. Efficient compression, which reduces the model size and memory footprint by up to 4x. Faster interference improves the interference speed due to lower complexity calculations with the quantized weights. Then there is hardware friendly. Yes, it is optimized for efficient hardware accelerators, maximizing its performance gain. It will have its, what we can say, it is hardware friendly. AWQ is a powerful technique that optimizes LLMs for efficiency without sacrificing the model accuracy. Okay. So by considering the data distributions in the activation, it tailors the precision of the weights to the specific characteristics of the model's input data. This approach not only reduces the memory and computational requirements of neural networks, but it ensures that the model remains accurate and robust in varieties of real-world scenarios. Then there is distillation. So there is knowledge distillations. So knowledge distillation is performed more commonly on neural networks associated with complex architecture. Okay. So firstly, we'll see what does knowledge distillation do. So it is a technique used to compress the neural networks. It involves training a smaller, more efficient models. For example, as we can say, student model to replicate the behavior of the larger, or what we can say, a pre-trained model, as in called as teacher model. Okay. So here we are using a deep learning as an advance, particularly in areas like speech recognitions, image recognitions, and natural language processing. The need for more efficient models has grown. Knowledge distillation has become popular because it allows smaller model to achieve the performance level close to that of the larger model as well, making them easier to deploy in the real world applications. Okay. So here, what we are doing, we are making a teacher model and the student model. Teacher model is a pre-trained model, and student model is smaller, efficient, more efficient model, and what we can say, it has been trained on smaller data sets. So it has smaller parameters. Okay, so this is a teacher and student model. Imagine a large pre-trained deep learning model as a teacher. This model is highly accurate, but it's bulky, requiring lots of computational resources and storage space. And then there is one model which is student model. We then create a smaller, simpler model called as student. This student model has fewer parameters and is therefore faster and more lightweight. So our knowledge distillation systems consist of three principal components. First is our knowledge. Second is our distillation algorithm. And third is our teacher-student architecture. So knowledge includes learned weights, biases, logics, activations, and relationships in the neural networks. So we will first see the types of knowledge. The first is our response-based knowledge, which focuses on the final output layer, uses the distillation laws to mimic teacher predictions. It uses the soft targets. Often it is used in image classification. Then there is feature-based knowledge. It utilizes the immediate layer feature activations. It is trained on student to mimic the teacher's feature representation. Okay, so first is our teacher model and second is our student model. It is used for mimicking the teacher's model. Okay, then there is relation-based knowledge. So it will capture the relationship between feature map. It is modeled as correlations, graphs, similarity matrix, etc. Then there is training methods. How we are going to train it? So there is offline distillation. Common methods with a pre-trained teacher guiding the student. Online distillations, like simultaneous updates of teacher and student models. It is efficient with the parallel computing. Okay. Then there is self-distillation. Teacher and students are the same model. Knowledge transfer from deeper to shallower layers. Then there is architecture. Design is critical for efficient knowledge transfer. Then there is common student model architecture, such as shallower versions of teacher with fewer layers, or we can say fewer neurons. Then there is quantized version of the teacher. Then there is smaller networks with efficient basic operations. Then there is smaller networks with optimized global architecture. Then there is same model as a teacher. Then there is neural architecture search for optimal design. So this is the complete algorithm for knowledge distillation. So first, what we are using? We are using the adversarial distillations, which will utilize our learning principle. Generator models creates the synthetic data. Synthetic means false data, close to that of the true distributions. Discriminator model will discriminate between the synthetic data and authentic data. Okay. Then there is applied to knowledge distillations for better representations. Okay. Then there are three methods, like synthetic data generation, like false data generation. Discriminator will generate whether it is in real data or a fake one. And there is online distillation. Okay. Then there is multi-teacher distillation. Student model learns for multiple teacher models. It will assembles of the teachers, provides diverse knowledge. Knowledge combined as an average response across the teachers. Okay, the knowledge combined from average responses across all the teachers. Okay, then transfers of logics and feature representations. Then there is cross-modal distributions. This cross-modal distribution, teacher trained in one modality. It will transfer the knowledge to the students in different modality. Okay. It addresses the lack of data or labels in a specific modalities common in the virtual domains. For example, we can say image to text or image to audio, like that. Useful for applications like visual question answering, image captioning, like that. It can be used for. Then there is others. So in others, there are, apart from distillation algorithm discussed above, there are several other algorithms also which have been applied for knowledge distillation. Graph-based distillation captures intra-data relationships using graphs instead of individual instances knowledge from the teacher to the students. Okay. Graphs are used in two ways, as a mean of knowledge transfer and to control transfer of the teacher's knowledge. Okay. Then there is in-graph-based distillation. In each vertex of the graph represents a self-supervised teachers, which may be based on response or feature-based knowledge like logics and feature map respectively. Then attention-based distillation is based on transferring the knowledge from the feature embeddings using the attention maps. Then there is data-free distillation. Data-free distillation is based on the synthetic data in the absence of training data sets due to privacy, security, or confidentiality reasons. The synthetic data is usually generated from teacher representations of pre-trained teacher models. In other applications, GANs are also used to generate the synthetic data. Okay. Then there is quantized distillations. Quantized distillation is used to transfer knowledge from high precision teacher models. Like, for example, 32-bit floating points to low precision student networks like 8-bit. Okay. For example, for the student networks like 8-bit. Lifelong distillation is based on learning mechanisms of continual learnings, lifelong learning, and meta learning, where previously learned knowledge is accumulated and transferred into the future learnings. Then there is neural architecture. Neural architecture search-based distillation is used to identify suitable students model architecture, which is used for optimizing the learning from the teacher's model. Okay. Then there is benefits of distillation. So we'll see the benefits of distillation. So it is used for reduced the model size. So firstly, the student model can be much smaller and faster than that of the teacher's model. Then the advantage of doing so is the reduction in the size makes the student model ideal for deployment on the source constrained devices such as smartphones also in edge computing platforms, allowing for efficient interference without requiring the extensive computational resources. Then there is improved accuracy. Yes. So knowledge distillations can enhance the accuracy of the student model. Okay. Then there are certain advantage of this. By learning from the teacher, the student models can get insights and knowledge that it might not acquire from the independent training itself. This can lead to better performance on the target task compared to that of the student model alone. Then there is flexibility. So, a knowledge distillation is a versatile and can be applied to a wide range of deep learning models and tasks. So, the adaptability allows the practitioner to leverage the knowledge distillations across various applications, like for image classification to natural language processing. It will facilitate the improvements in the model performance and efficiency regardless of specific domains. Then there is pruning. So firstly, we will understand what is pruning. So pruning is a technique used to reduce the numbers of parameters in the deep learning, in the deep neural networks. Okay. By identifying and removing the redundant or unimportant parameters, pruning helps create a more efficient models without significantly affecting its accuracy. Okay. So what we are doing here, we are removing some of the redundant or unimportant parameters from our deep neural networks to increase our accuracy. Then how pruning works. So pruning works on identification of redundant parameters. So during or after training, the model is analyzed to determine which parameter contributes the least to its performance. This can be based on its weight, where smaller weights often indicate less importance. Okay. Then there is removal of parameters, or what we can say strategic removals. Once the redundant parameter is identified, once we identify, no, this is this we can remove also. So once the redundant parameter is identified, they are removed from the network. This can be done in various ways, like such as zeroing out weights or completely removing the entire neurons or layers as well. Then there is types of pronings. So in types of pronings, we have pruning results in compressed models that runs faster. It reduces the computational cost involved in in network trainings and reduces the overall model size, which is importantly, it saves the computational time and energy as well. So a model can be pruned during or after the training. Various techniques exist for this pruning process. Some of these are like weight pruning. Weight concentrations that are below some predefined thresholds are pruned, like zeroed out, as I have told earlier. If we want to if we want to remove some of the redundant parameters from the neural networks, we can use the weight pruning, where it will directly zeroed out that parameters. Then there is neuron pruning. Instead of removing the weights one by one, which can be time consuming, we can prune the neurons. Like we can delete this, and this 2 has been deleted from, this 2 is neuron which has been removed from this parameter. Okay. Then filter pruning. Filters are ranked according to the importance, and the least important filters are removed from the networks. Okay. Suppose this is our input image, which is 4 by 4 by 3, and we are using our filter of 3 by 3 by 3, and here we are using a filter of 3 by 3 by 3. Okay. So once we are using this, the importance of the filters can be calculated by using the L1, L2 norm. Okay. Then there is layer prunings. So layers can also be pruned. Okay. So for using the layered pruning, what we can do here, that this technique involves removing the entire layers from the neural networks. This is typically done when certain layers do not contribute significantly to the model's overall effectiveness, or when the architectures can be simplified. So layer prunings can lead to significant reductions in both like model size and computational loads, but it requires careful considerations to avoid degrading performance. Then these are some of the benefits of pruning, like reduce the model size. Okay. So if we want to decrease the memory, we want to decrease the memory requirements by removing unnecessary weights and what we can say parameters, pruning effectively lowers the amount of memory needed to store the model, making it more lightweight. Then there is faster model loading and interference. A smaller models can be loaded into memory more quickly. Yes, a smaller model can be loaded quickly as compared to that of the larger models. So, and the interference process becomes faster due to fewer computations also, since the smaller model will have lesser parameters as compared to that of the big models, larger models, we can say. Then potential for deployment on devices with limited resources. Yes, we can use as we are reducing the model size, it will make feasible to deploy the neural networks on devices with constrained resources, such as smartphones also, IoT devices, and edge computing platforms. Then there is potential performances. So, in some cases, pronings can even boost accuracy by mitigating overfitting also. If it is having some overfitting, it can mitigate that also. So, what we can say, pruning can enhance the model accuracy by reducing the overfitting, by eliminating the unnecessary parameters. Since it will run again and again, and it will, so that the model may generate better to unseen data. Okay. So overall, what it will do, it will increase our model's performance. Then there is compatibility with other techniques, like combinations with quantizations and knowledge distillations. Proning can be effectively combined with other optimization techniques, such as quantizations, which is used for reducing the precision of weights, and knowledge distillation, which is transferring the knowledge from larger models to the smaller one. So this synergy can lead to even more efficient, or we can say more good model that retains high accuracy while being optimized for speed and resource uses. Okay. So this is it. So let's make a quick recap of what we have understood about model compression. So in model compression, what we have seen, so model compression is a critical techniques in the world for artificial intelligence, where we have seen that if we want to reduce the size and complexity of the model, while we don't want to we want to minimize the impacts on its performance as well. Okay, so for that we can use these techniques. So we have understood about the quantization techniques. So quantization techniques we have understood. Here we have seen a quantized model excludes some or all the operations on the tensor, which reduce the precision. Okay. Then we have understood about how the quantization works. We have understood about quantization aware trainings, dynamic quantizations, understood about the post-training quantizations. GPTQ we have understood. Then GPTQ is a global post-training quantizations, which is a techniques applies for quantization after the model is trained. Okay. Then we have understood about GPTQ, GGUF. GGUF is a global gradient uniformity framework, which is a newer method which focuses on preserving the gradient uniformity during compression to maintain the model accuracy. Then we have understood about AWQ. So AWQ is an activation aware weight quantizations. So this technique will consider the activations while quantizing the weights, which will lead to more accurate comprised, what we can say, leading to more accurate comprised model. Then we have understood about distillation. Distillation is a student-teacher architecture. Okay, here what we are using here, we are using a smaller model, which is a student model, which will learn to mimic from a larger models, which is a teacher model, which will achieve the similar performance with lesser complexity. Then we have understood about pruning. At the last, we have understood about pruning. Pruning is a technique which removes the less efficient part of the model, which will result in a leaner structure without sacrificing too much accuracy. So this is it. This is it. We have understood about several techniques, model compression techniques like quantizations, operator quantizations, GPTQ, GGUF, AWQ, distillations, and pruning at last. Okay. So this is it for model compression. We will see you with next topic, newer topic. So this is it for today. Thank you for joining.